Mary Montgomery, homework 2, part 1, question 1, interpolated star. We start with our vertex structure, which is just a position and a color. Make sure it matches our input layout. Then we look at the vertex buffer. We have a star pattern that contains 6 separate triangles, north, south, east, and west pointing triangles, and then the 2 central triangles that make up the center square. All of the bottom vertices of all the triangles are yellow, which means we don't have to remake any vertices for the square since the positions and colors of those will all be the same. So we have the 12 total vertices, so we update the byte width with that 12 number. Next, we update the index buffer. Again, we can repeat vertices because they are the same position and color. Update the byte width with the new number of indices, and update the same new index count as the first param of our drawIndex function. Looking at part 1, question 2, solid star, we have the same vertex structure with position and color. Make sure our input layout stays the same. Now the vertex buffer is the only thing that changes between question 1 and question 2. We still have our star pattern with our 6 separate triangles. The 2 central triangles make this yellow square, but we can no longer repeat vertices to make this central yellow square as with question 1. Now these vertices are different due to their different color, even though they share the same position. So instead of getting an interpolated color with the lime, yellow, yellow, now we need lime, lime, lime to get this solid color, meaning we need these 4 extra vertices now. They are different because they have a new color, the color yellow. So with this addition of these new square making verts, we need to add those 4 verts to this byte width. Now we have 16 total verts. Down here, our index buffer, we no longer repeat those vertices, so we have our new vertices listed in a counterclockwise order, of course. Our byte width, still the same number of triangles, so it's still 3 times 6, which is again visible here with our total index count for the drawIndex prim. Looking at part 1, question 3, simple vertex structure change. We are told to change the structure of simple vertex from position color to color position. We are told to mirror that in the vertex buffer now, to have color position rather than position color. When we ran that, it created an empty viewport, meaning something was going wrong. What we also needed to change was the input layout. Now we can run it and it works, but we needed to switch this input layout from position color to color position to mirror the structure of the vertex. We also had to update the 5th parameter, which is the byte offset, since now the color has no byte offset and position has a byte offset of 16 due to the size of the color vect. Looking at part 1, question 4, dynamic color star, we were given the struct of the simple vertex, which now instead of a position and color where color is a vect, it is position color num, where color num is an int, and this int will allow us to dynamically change the color of our vertices through this constant buffer structure that we were also given. This is an array of color vects that can be referenced using simple vertex's color num. So we have a vect of colors of length 2 starting off. We were also given code for the constant buffer color, which is how to set the color dynamically through the constant buffer. We have our 2 color values, which right now are set to yellow and red. Then we have this update sub resource call, which updates the constant buffer color. Now starting from the top of what I did, I defined a new input layout since the layout needed to change to account for the int color num. Now the second element of the layout is no longer just color vect, it is labeled with semantic color num, and it is of the DXGI format R8uint, which is an 8-bit unsigned int, which is what color num is for our input layout. Next we had to change the vertex buffer. I'll run the program so we can see it. We still have the same 6 triangles that we've had for the last few problems, but this time, instead of position, comma, color vect, we just have this color num, which is in reference to the index of our color constant buffer, which color it's referencing. So all the triangles are one color. The inner square is a different color, as we can see in our example. The byte width of our vertex buffer is still 16 vertices. Next is our index buffer, which didn't need to change. We still have our 6 triangles. The byte width of our index buffer is 3 times those 6 triangles. And here's the main new code. We have to add the constant buffer. So we're adding it onto the buffer descriptor BD. We need to define this new usage and define the byte width as the size of the color struct, set the bind flag to bind to our new constant buffer, and then the CPU access flag is set to be 0. Next, we try to connect the device to the constant buffer. So we create this buffer with our new constant color buffer and assert that this succeeded. Next, we set the immediate context constant buffer. I'm using the PS set constant buffer, not the VS set constant buffer, because I'm changing the color in the pixel shader, not in the vertex shader. So here's where I set this pixel shader constant buffer to be our new color constant buffer. And we already went through this, and the last thing to change is just this draw scene, make sure our draw index, again, accounts for the 6 triangles. Next, we changed the simple color plus HLSL file. We had to update the vertex data and pixel data structs to match our input layout defined in our input element descriptor layout array, meaning we needed to float for position with the semantics matching what's in our layout, which is position, and our int color num with semantics matching also in our layout param color num. So we have those. Now we need to set up the shader constants for the constant buffer. We should register the new buffer, so this B0 indicates it's the 0th constant buffer, and this matches our struct for our CB color. We have this float4, which is a vector of our active colors, and it's size 2. Next is the vertex shader, which I didn't change since I'm changing the color through the pixel shader. And finally, we have the changed pixel shader, which now has 2 inputs, the position and the color num int. So we return the correct color using the color num param, this integer, and the color array active call, which we defined up here. Now back in our DX app, we will show that this is working as it should by changing the colors. We can change the inner square to green and the outer triangles to magenta. Save it, run it, and we will see that it is dynamically changing the colors. For further work question 1, what's the difference between constant buffers and shader constants? Well, constant buffers definition from the textbook. Constant buffers are just blocks of data that can store different variables that may be accessed by a shader. They are a GPU resource, but they can be changed at runtime by the CPU through a handle. They are constant by having a constant value during the single execution of the render pipeline. The buffer connects to the render pipeline through a shader constant. Shader constants are what the data that gets committed into the constant buffer maps to during one execution of the render pipeline. Or as Microsoft put it in How to Create a Constant Buffer webpage, constant buffers contain shader constant data. Looking at further work part 2, we were told to add this code to our pixel shader. The intent of the code is to add more white to the pixels the further away from the triangle center you go, which includes whitening the background. However, the result is just a triangle with lighter corners and the same monochrome blue background, as we can see here. We can see in the code in our dxapp.cpp file that the pixel shader is applied to the device through this call. On our immediate context, we take the pixel shader and set the shader to our pixel shader. The pixel shader stage of the rendering pipeline comes directly after the rasterizer stage of the pipeline. If a pixel shader is defined, the rasterizer stage invokes a pixel shader once for each pixel covered by a primitive. In our case, this means that the pixel shader is invoked on the triangle primitive only. The pixels that make up the viewport, the blue background, are drawn separately on the back buffer with this call, our immediate context, clear render target view, with our background color. This call is made before we call the draw index functions, which is what draws the triangle from the stored index and vertex buffers after the rasterization and the pixel shader stage, which have already changed the color of our triangle and not changed the color of our background.